Okay, thank you, Marcelo. Okay, today I will discuss the problem of defining entanglement in the case of indistinguishable case, because I don't want to talk about particles now. This paper is in collaboration with Sebastian Fortin, who is here, so we can share the answers of the questions. And well, the outline of the talk is this. It's very simple. First, I will state the problem. Then I will very briefly recall some reactions to the problem. And this will lead me to introduce the ontology of properties in a very, very intuitive way. And from the basis of this, I will discuss indistinguishability in this kind of ontology. So finally, I will discuss entanglement and indistinguishability in an ontology of properties. So let us state the problem. Well, we know that the state of a composite system is entangled if it is not factorizable in terms of the product of the states of the component systems. In general, this is the definition in the case of n equal 2. In the case of two fermions, we should say that this is not entangled, but we cannot say that because we know that this state must be antisymmetrized. So we obtain, in this particular case, for instance, we obtain a state of this way, in this form, and in this case, the state is not factorizable,
No te están pasando las diapositivas.
No están pasando.
No.
Ops. No están pasando.
Deja de compartir y compartir de nuevo con.
Empezamos de nuevo. Empezamos de nuevo. The first time that they have problem to
try now.
Hey, this way.
This
¿Se
is
está
the first
moviendo?
one.
No,
only the first one.
No se está moviendo.
Tenés que poner pantalla completa y después compartir.
A ver, en general lo hacía al revés yo. A ver. No, es que si hago así no puedo presentar. No puedo compartir. No tengo manera de ir a compartir. Bueno, lo vemos así.
Sí.
Lo vemos de esta manera. This way. So now you can see the screen is moving now.
Yes, it's moving.
Okay.
Now it's moving.
Sorry. So this is these are the steps of the presentation. And now I begin by stating the problem, and the problem is how to define entanglement in the case of indistinguishable particles. And if we have two fermions, we know that we have antisymmetrized the state, so we obtain the state of this form, and this state is not factorizable, but I mean, now the question is, what happened with this state? In a recent paper, Mueller and Littwater called this kind of state tangled. I mean, states that are not factorizable because of symmetrization or antisymmetrization. So the problem is to know or to answer the question whether tangled states are entangled or not. So which are the better known reactions to the problem? In very, I mean, traditional paper, Lévy-Leblond says that tangled states are entangled. Some people think that because they are not factorizable, they are entangled. But the problem is that tangled states do not give rise to the correlations that we expect to violate Bell's inequalities. The probability distribution associated with them factorizes. They are fully compatible with local hidden variable models, and they cannot be used as resources for quantum information as legitimate entangled state. I mean, they can be used, but not in the same way as legitimate entangled states. In a very, very well-known paper by Girardi, Marinato, and Weber, they clearly say, not with this terminology, because they don't use tangled, but they are saying something that can be said in this terminology, that tangled states are non-entangled. Which is the criterion that the authors use? They say that two systems are non-entangled when they possess a complete set of properties. In this sense, they say that even if one cannot say that particle 1 has a complete set of properties and particle 2 has a complete set of properties, because we cannot use labels 1 and 2, therefore, we can say, meaningfully say, that there are two particles, each one with its complete set of properties. Another reaction to the problem is that given by Ladyman, Linevo, and Bigach in a previous paper of that named that tangled, and they say that the entanglement of tangled states is really apparent and has no physical significance, because it is just a result, an artifact of a surplus structure of the Hilbert space formalism. The fact that we need to let aside the non-symmetrized states or non-antisymmetrized states. So instead of using a tensor product, they use a wedge product. I will not define this here, but it's well defined. I mean, it's well defined. So they prove that if I take something like this, a tangled state like the one I began, that is clearly, I mean, tangled, obtained, I mean, it is not factorizable because of antisymmetrizing. If I translate it in terms of the wedge product, I obtain a factorizable state. I mean, I can factorize the state in terms of the wedge product. So instead of thinking of factorizability in terms of the normal product, they use the wedge product, the normal tensor product. Now, all these views have a common feature, that is that indistinguishable is considered as a relation between particles. What is, they are, I mean, particles of the same type used by philosophers, or identical particles as physicists used to call them, but it is a relationship between particles. And the shortcoming in our view is that they treat distinguishable case and the indistinguishable case in different ways. I mean, the question is that if we can offer some framework that supplies a unified view valid for both cases, the indistinguishable case and the indistinguishable case, and this is what we try to offer with our proposal. So what is our ontology of properties? When we work in a Hilbert space formalism, the system is represented by the Hilbert space, and we have the primary elements are states of systems, states of particles, and secondary elements are observables which are applied to states, and they are considered as properties of systems. In the algebraic formalism, the thing is the reverse. Systems are represented by a star algebra of observables. So The primary elements are the observables, the properties, and states and secondary elements, which are only expectation value functionals on the algebra of observables. I mean, their role is to compute expectation values. They have no other meaning, ontological meaning. So the Hilbert phase formalism with states attached to particles and observables as properties suggests an ontology of individuals and properties, a traditional, say, Aristotelian, if you want, or Lockean ontology. The algebraic formalism, on the contrary, suggests an ontology of properties, where properties are primary, and in any case, if we can talk about objects, the objects that are, if you want, bundles of properties. So we are based on the algebraic formalism, and the idea is intuitively this way, this one. Let us suppose that we have a system that is a non-individual bundle of properties. It's a bundle of, we can discuss later. It's a bundle, but it's not like a traditional bundle theory where bundles form individuals, because if they were individuals, we had the same problems as always in quantum mechanics with the concept of individuals. So these are completely bundles that are not individuals at all. So they have no principle of individuality. I mean, they have not a principle that gives them synchronic identity nor diachronic identity. They have no individuality principle that make them different than another bundle and different from the same bundle in different times. The same bundle. I mean, that may let you identify the bundle in different times, as in happening in quantum mechanics. So now, what is indistinguishability from this view? If we have indistinguishable bundles, now the colors and the symbols are very trivial. I mean, the same color is the same. A color is represents an observables, and the symbols the eigenvalues. If we have indistinguishable bundles, so when we form a new, when they come together to form, to combine and form another system, that system is a new bundle where the original bundles cannot be re-identified. So this is a single, a unique entity where the identity or the individuality of the original bundles gets lost. I mean, they don't get lost because they were not individuals from the very beginning. They are completely and absolutely bundles. So the peculiarity of the case when the bundles are indistinguishable is that this new bundle now is symmetric, just by construction. So in this case, when we think about the principle of identity of indiscernibles, the Leibniz principle that is very discussed in the case of quantum mechanics, the principle says that two individuals that have all the same property, all the properties in common, they are the same individual. This principle is not false. The fact is that it does not apply at all, because indistinguishability is not a relation between individual particles. I mean, the principle of identity, the Leibniz principle, is a principle that applies to individuals. Those individuals designed by these individual variables, precisely logical individual variables. So now we have no individuals, so the principle does not apply, because indistinguishability, that is not a relation between individuals, is an internal symmetry of a single composite bundle. So it changed indistinguishability changed its meaning from the very beginning. What happened with indistinguishability? So in this ontology, let us assume that they are not, that systems are not individual but bundles, and they are represented by spaces of observables. And if we make an aggregate of two bundles, we form another bundle whose observables have this form, and this is the general form of a generic observable of the composite bundle. But the fact is that the operation of aggregation of bundles, when it is applied of indistinguishable bundles, is commutative. This is very natural. If the bundles are indistinguishable, it doesn't matter which I take first and then which I take later, so I can permute the order in which I take them. So this led to the fact that any observable of the new bundle must be represented by this symmetric matrix with respect to the permutation of the indices alpha, beta, m, and n coming from the two original bundles. So again, indistinguishability is no longer a relationship between individual particles, but an internal symmetry of the whole closed system that is manifested by the fact that its observables are symmetric. What about symmetric states? Let us consider states, density operators. Any operator can be written as a sum of a symmetric part and anti-symmetric part. This is the meaning of symmetric part and anti-symmetric part. So when I make the expectation value of any observable of the system, the composite system, the system composite of indistinguishable bundles, and I make the trace, when I decompose the state into the symmetric and the anti-symmetric part, the anti-symmetric part has no effect on a symmetric observable. This is a mathematical result, of course. An anti-symmetric operator on a symmetric operator, the trace is 0. So the fact is that the symmetry of the operators representing physical states of aggregates of elemental particles, bundles composed of original bundles that are indistinguishable, is not the result of an ad hoc symmetrization, but it's due to ontological reasons. That is the very structure of the ontology that makes natural that indistinguishable bundles, when composed, can be permuted. So how to understand the indistinguishability principle in this case? The traditional formulation of the indistinguishability principle is in terms of states. For any state of a composite system whose components are indistinguishable particles, the expectation value of any observable must be the same for that state and for the permutation of the state. This is the normal or traditional formulation. Nevertheless, this form of the principle establishes a restriction on the states of the composite system. On the other hand, the principle can be formulated in terms of observables. For any observable of a composite system whose components are indistinguishable subsystems, in this case, bundles, its expectation value in any state must be the same for that observable and for the permutation of that observable. In this case, the principle establishes a restriction on the observables of the composite system. I have to retain only the observables that are symmetric. And this is something that it's in the literature of the subject. I mean, we are not inventing this formulation. What I mean is that from the viewpoint of an ontology of properties, this is not the version of the principle that makes sense, but this one is the principle that makes sense in this context. So, what happened with entanglement and indistinguishability in this kind of ontology? What happened with entanglement is something that when this point is discussed, when entanglement in distinguishable particles is discussed, these general features of entanglement are usually not taken into account. Let us take them into account. First, interaction is not a requirement for entanglement. We know that there is entanglement swapping. Entanglement is not a relation between particles. This is something that there is very clear in the literature, in the physical literature. There is intraparticle entanglement. And entanglement, there is entanglement of, by contrast, in general, people talk about entanglement of indistinguishable particles by contrast with these results in physics. And more important, entanglement is relative to the particular decomposition of the composite system. For instance, in a very cited paper, it is said, entanglement is a property of a quantum state relative to a given set of subsystems. A question like, is there entanglement in such state, is meaningless in isolation. This is something that has been discussed, for instance, by John Ehrman a lot, not in the case of distinguishability, but in the case of definition of entanglement. So the problem is that in the case of indistinguishability, we have no tensor product structure. So this is the problem in this case. So these kind of features are not taken into account in the discussions about entanglement and indistinguishability in the philosophical literature. So we want to take into account and show that from the viewpoint of an ontology of properties, these are normally taken into account. From our ontology of properties view, entanglement, we say, is not a relation between particles because there are no particles. Systems and subsystems are bundles of properties. So entanglement is given by a kind of correlation between properties, not between systems. Entanglement is relative to the decomposition. Which decomposition? The composition of a system, but the system now is represented by an algebra of observables. So entanglement is relative to the decomposition of an algebra into some algebra of observables. And this kind of algebraic approach to entanglement is something that is present in the physical literature. For instance, there are two papers by Balachandran and collaborators, but since then it was presented in other papers. And the idea is that instead of talking about reduced state, the reduced state needs to use, we need a Hilbert space structure to define a reduced state they replace the idea of reduced state by the idea of restriction to a subalgebra. A state is a restriction to a subalgebra when this happens. I mean, the expectation value in this in the original state is the same as in the restricted algebra in the restricted state. I mean, the idea is to use, in a certain sense, the very definition or the main idea of the reduced state, but not with the definition of the reduced states in terms of Hilbert space. I mean, in terms of operations on the Hilbert space, on states of the Hilbert space. So, with this definition, a pure state on a certain algebra or subalgebra is not entangled with respect to the partition, no, in terms of a certain algebra, to the partition, sorry, this should not be the one, to a certain partition if the restrictions are also pure. The idea is that instead of thinking about reduced states with the traditional definitions or traditional ways of computing and say, if the reduced states are pure, so the states, the composite states is not entangled. In this case, we use the concept of restriction or to a subalgebra that is a generalization for a partition of complete algebra in subalgebras. In this case, we have no problem if we have not the structure of this Hilbert space. We have a structure that we have not in the case of indistinguishability. So, which are the conclusions? From this viewpoint, entanglement is not a relation between particles, but it is a specific property of the state of the whole composite system that encodes particular correlations between properties, those correlations which violate Bell's inequalities. Indistinguishability is not a relation between particles, but an ontological motivated symmetry of the whole composite system. So, in the case of indistinguishability, entanglement does not require the symmetrization of the state. We have the symmetrization of the observable, but this is due to ontological reasons. It's not an ad hoc symmetrization or anti-symmetrization of the states. And this gives a unified view of entanglement. Thank you. These are papers on the ontology of properties, previous papers here, and this presentation is based on this this last paper that I hope that very soon will be published in Studies in History and Philosophy of Science in the section of physics. So if somebody wants to read it before publication, I can send them. Thank you.
Okay, thanks Olympia for your talk. Now we have time for questions. Anyone have a question?
I can stop here.
Okay, Dennis.
Thank you, Olympia. Very interesting talk, and you will not be surprised that I agree with many things that you have been proposing and saying. I've actually several questions, but the first question is, you want to do without any particles, and you want to replace the particle concept with a bundle of properties. But I was wondering when I saw your presentation whether you don't assume something like a particle already from the start, because you seem to think in terms of an algebra that's split up in sub sub-algebras, and all these sub-algebras will bind certain operators and properties together. And normally, one would call such a sub-algebra as something that corresponds to a physical system, and in particular, a particle. So don't you smuggle in the concept of a particle via the back door?
Thank you, Dennis. Thank you. This is a very good question. When I talk about particles, I'm thinking about individuals in the philosophical sense. I mean, we have systems, but those systems do not behave as individuals, as traditional individuals, so that you can put them together and then re-identify them in the composite system, and then that you can count them in the composite system, and that you can re-identify them through time, and that you can label them. So all these traditional, classical views, the classical features are not present in this case. So we can talk about particles, but we have to clarify that they are not classical particles. They are quantals, if you want. This is why I talk about systems and not about particles, because when we talk about particles, it seems that we are talking about objects. There is something very interesting that about how to talk, how to formally handle this kind of items that are not objects in the classical sense. And well, we are trying to, we have written a paper, and we have trying to finish it, trying to use quasi-set theory to treat not as originally, this is a paper with Decio Krause and Federico Holick and Juan Pablo, but the point is that we are not using the quasi-set theory as originally Decio Krause does, but the items are not non-individuals representing systems. The items are properties. So when I talk about a bundle of properties, this is a quasi-set, because we have not even a logical language to talk about properties in this way. I mean, and we needed, even if we think like your talk the other day, we think in substances, mass, the reference of mass terms. We also need a kind of new logics to talk about this. It's completely different from traditional individuals.
Okay. Thank you, that helps. Can I ask something else, or is that...
Yeah, you can.
Oh, yes, one other thing. So you derived, as a kind of very plausible and natural thing within this properties framework, that all the states, I mean the density operators, the density matrices, must be symmetrical. But it seems to me that that's weaker than what's used in the ordinary particle picture, where you have fermions or bosons, and the states of the one are anti-symmetrical and the others are symmetrical. But if the total states, I mean the density matrices, are symmetrical, I think there are more possibilities than these two things.
Well,
So
we are not considering parastatistics, but the case of symmetric states or anti-symmetric states both give symmetric operators. The symmetric operator can come from a symmetric. I mean, you will have symmetric observables which are fermionic and which are bosonic. This is, I mean, it's a subtle point, but both as observables, I mean, as operators, are both symmetric, but they operate in a different way if they are bosonic or if they are fermionic. But as operators, they are both symmetric as operators.
Yeah, sure. Yeah, so I understand, right? So do you understand that you do not exclude, or you cannot exclude on the basis of your formalism that there are states that are either symmetric or anti-symmetric?
No, I will send you the paper. This is very well explained there. Yes. No, we don't exclude that. No. Thank you.
Thank you very much for your
the opportunity to explain that.
Thank you.
Okay, we have another question from Ariel Caticho.
Okay, very good. Sorry, but I don't have a camera right now. I will on Friday when I give my talk. Let's see. I was just curious. All this discussion about indistinguishable particles, particularly fermions, is based, or rather becomes confused by the fact that these are supposed to be indistinguishable objects, and you have a Pauli exclusion principle and all of that. Good. Have you, this is what I'm curious about. Have you considered the possibility of using something like a field definition of fermions, something along the lines of what Jordan and Wigner did back in the day, in which the model one uses to describe these fermions is almost like a space is like a computer screen. Each volume element is a pixel. The pixel can be on or off, but it can only be on once. You cannot put two ons on the same pixel. It's either lit or not. It doesn't make any sense to have two of these particles at the same pixel. So this would be a model in which the exclusion principle is automatically taken into account. Obviously, the system is the whole of space, the excitation of the whole field, the state of all the pixels. And so I was wondering if you have thought about, your formulation in terms of the ontology of properties in such a system where the concept of particles emerges, but not emerges in the philosophical way, but there is a concept of particle in which each pixel is localized, but the identity makes absolutely no sense. They're automatically indistinguishable, right?
Yeah.
Have you thought about those lines?
Well, thank you for your question, because it allows me to say something more. I don't know. I never heard about that model, but I think that model is to explain the exclusion principle. But the fact is that our view applies to fermions and to bosons. So this is not the problem of the exclusion principle. It's the problem of indistinguishability. Nevertheless, what you say about the excitation of the field, this is very relevant, because this view, this proposal is a proposal for interpretation of non-relativistic quantum mechanics. It's not, I'm not talking about quantum field theory. Nevertheless, I think that it is much easier to extrapolate a view of, yes, a picture of an ontology of properties to quantum field theory than an ontology of particles. Because if I have an ontology of properties, now I can think that properties are, properties are functions of point, of space-time point. So now I have, instead of having an operator, I have an operator that it's a field, and the particle, I mean the electron, is a field. I mean, it's a property. It's a property for each. No, a property, bundle of properties, but the properties depend of each point of space-time. And this is not crazy, because there is an interpretation of quantum field theory in terms of bundle of properties in the field of philosophy of physics that was this. I mean, I think that it was some years later of our first paper on our interpretation, but we can say that it was pretty simultaneous. So the idea that quantum field theory is more friendly to an ontology of properties is not. I mean, it's not very natural, but I think that it's natural. So if we take the interpretation of an ontology of property from the very beginning, just in the case of non-relativistic quantum mechanics, to go to quantum field theory, I think that it's easier. So thank you also for your question, because it allows me to say.
Okay, no, thank you.
Thank you.
I also agree that it is actually easier to think in terms of fields, whether you're talking about bosons or fermions, that somehow it is the particles that are the less fundamental objects here.
Yes. And it's interesting, but what is a field? A field is something that assigns properties of each point of space-time.
Correct. Yes.
So it's so natural to pass from properties to fields understood as properties on the space-time.
So then in this case, your properties would be like functionals.
Yeah.
Over distributions in space-time, which is perfectly nice. Yes.
Thank you.
Thank you.
Thank you.